My Felix is like, yeah, I'm just like, you guys
Watching the running this one, I was just when it asked, so it's basically asking to calculate the percent error between the initial equilibrium pressures by hydrogen sulfide, and I did it 2 different ways, and both came out wrong, so I wasn't really sure, how to go about that.
And the changes would be neglected. So what do you do? I want to see your problem.
So what I did was I used the percent error formula, theoretical minus experimental divided by theoretical times 100. So I did 8.29, which is the initial minus the equilibrium concentration, 0.4, which gets you this value, 0.05, and then I divided that by the initial concentration, and that gets you 1.81% as well. And then the second time, so that's like a relative percent error, and the second time I tried doing like absolute percent error.
Is this homework or thing?
It's the homework. Yeah, I know like the point, it's still a little point, so it really doesn't matter, but
Yeah.
just in case it shows up.
So I think it's actually you calculate the use actually small approximation here.
Yeah.
Okay, so I think how you want to compare to this actually you use small as that one you can without. You calculate the difference between the yeah, say starting from here and then especially don't use small as a approximation that's real.
So I thought about that, and if you don't use the small approximation, you end up with a cubic formula, which you can solve the quadratic. And there's no real like analytical way to say. I can find what I mean, like you get 4x squared times x divided by some value squared. So you end up 4x cubed divided by some square. So I know there is a cubic formula, but extremely long. I've also just plugged it into Cosmos.
Yeah, why don't you send me your work? Then I did not actually I did not encounter this question before, but it's actually my original thought. It's actually asking for the errors that's to see some concentrations so that would be associated error and go with it. Right. So I think you have to ask some error from there. But what you do is actually quite interesting. You actually do all this calculation and then and you compare your initial to the equilibrium concentration that actually comes to strange.
Yeah, but that's what it asks for. The percent error between the equilibrium and the initial trend.
Ah, okay.
Not between the.
So it's actually without the small population. So how do you get a 1.5 with the difference between and the difference is divided by that or divided by the.
Well, I divided. First, I subtracted them from each other. So for the H2S, it's minus 2x, the change, and 2x happens to be 0.0153. So that's the difference. And then I divided that by the original, which gives you 1.21%. And my first attempt, when I put in 1.81, it was correct.
The correct answer? I feel like actually, so you say you divided by 2.
Divided by 2?
So you say, so I guess that if this, okay, this structure like divided by lab of the number.
0.01805.
Yep, that's it. 0.3. Yeah, and then divided by lab. 0.018. Okay, so that's 1.8%.
Yeah, and that's what I did on my first attempt. The 1.5 was my second attempt, but the first attempt was 1.8%, and it was also. And you can look at.
Because it's been really, I feel it's like as part of the people are afraid to think about what it is. It's her. It's her. It's like romantic is part of it. Look back at the two counts.
Has been and sent it to me, so I can get discuss with someone. I don't think we did anything wrong. I don't think we did anything wrong. Yeah, like the one that we did, I think that there's nothing wrong with your calculation.
Also, by the way, talk to employees, both very highly reviewed, and especially the baselines.
Yeah, we can talk more in the future, okay?
Take a load on. At least we can stick your file, right?
Okay, so let's get started. Okay, what we're going to do today is actually we're going to finish chapter 12, and then we're going to enter this review hangout for the midterm one. Okay, so but before we go start, let's see any interesting questions here. I guess everything's actually normal. So, all right, so let's look at this first. So on the screen is actually the summary about your average grade for the homework and then the quiz. Okay, so I think we are actually doing reasonably well, but I'm a bit worried about this. Okay, so I think in general our section is actually doing pretty well, but if you belong to that group, I think we need to talk. Okay, the midterm one is actually coming, so after midterm one, there's pretty much no turning back. Okay, so if you don't do well in your midterm one, chances are that you won't do well until the end of the semester. Okay, so this week will be your last week that you have a chance to actually, working so hard that you can just still get something back. Okay, and then you can still get the grade that you want. Okay, so you need to actually really find a way that works for you. Okay, and then feel free to contact or connect with me to seeking for some professional opinions. Okay. All right. So today, any questions are for this? I guess I don't need to actually go through like what is the average score that we have so far. Okay. So if you look at these things, that is actually the range that we have. Okay. So in general, it's actually better than other sections. Okay. The very last thing I want to talk about today for chapter 12 is the Le Chatelet principle. Okay, for this idea, the concept is actually very simple. What the Le Chatelet principle tells us is that if you have a system that is already at equilibrium, if you change 3 things, okay, only these 3 things, nothing else, okay, which is if you change the concentration, you change the pressure, you change the temperature, the reaction will move to in a direction that's going to compensate your change. Okay, so let me say again, the Charlotte principle is that if your system is actually at equilibrium, you are going to do some perturbation to your system. 3 type of perturbation you can do to your system is actually change your concentration, you change your pressure, or you change your temperature. The reaction will move to a direction that's going to compensate all those change. Okay, so that is actually the basic idea of Le Chatelet principle. One thing you're going to see a lot in your quiz, okay, they try to confuse you is that they're going to give you the false option called the catalyst, okay? So if you see a question that belongs to the Le Chatelet principle and you see the catalyst as one of your options, please cross out that catalyst, okay? Because catalyst doesn't change the equilibrium, okay? So what does catalyst change? Yes, that's actually only one thing that catalysts do is change your activation energy. So you need to have a very clear idea that once you see this term catalyst, the only thing you need to associate with it is activation energy and vice versa. Okay, so don't get confused by this trap. Okay, it's something that you really don't want to fall into. All right, so with that concept, let's do the very final questions for this chapter. Okay, let's read through these questions carefully. Okay, consider the reaction N2 plus 3H2 that give you 2NH3, which is exothermic as written. What will be the effect on the equilibrium position? Okay, so this is actually a keyword. Equilibrium position. Okay, once you select keyword, it's 100% belongs to the Chatelet principle. Okay, so the only 3 things that's relevant to your Le Chatelet principle will be concentration, pressure, and temperature. All right, so those are the things that you should have in mind. Okay, so with those things in mind, then let's read these things again. Okay, so you have this N2 gas form plus 3H2 gas form will equilibrium with 2NH3 in the gas form, which is exothermic. What does exothermic mean? Release heat, right? So in terms of the writing the equation, this is what you should do, right? Okay, so you generate a product and also you generate a lot of heat. Okay, so the temperature going to increase, right? So you need to translate this word exothermic, then you know the heat should be appear on the right-hand side of the equation. Okay. Any questions for this? Okay, so if not, if the question says, okay, the reaction is endothermic, then what do you write? Where did you put your heat? On the other side, right? On the left-hand side, on the product side. Okay, if it's actually endothermic. Okay, so you should be able to actually put these things at the right location. Okay. So this is actually important because we are going to go through many different type of scenarios for this specific question. Okay. So if you read through this, it says like, what would be the effect on the equilibrium when removing N2? Okay, so when we say removing N2, what does it mean? It's going to affect which term? So we say there's only 3 terms you need to worry about, right? Pressure, concentration, and temperature. Concentration will be increase or decrease. Decrease, right? Because you're removing the N2 from your system, right? Therefore, the concentration will be decreased. Okay. And then some people will say, why not pressure? It could be pressure too, because your N2 is a gas, right? So concentration of the gas is actually proportional to the pressure. So it's actually equivalent. Okay, so if you have a gas system, okay, the concentration and pressure are actually the same thing. Okay, so what it says is actually, okay, I'm going to decrease this. Right, I'm removing, sorry, not H2, but N2, right? So the first one is actually, I'm going to removing N2 from my system. What it really says is actually, you can say the concentration of N2 or the pressure of your N2 is going to decrease, right? Okay, so what the general principle tell us is that, okay, if you make distance decrease, the direction actually move to a direction that's going to compensate that decrease or compensate that increase, compensate that change, right? Since right now you actually make this guy less, therefore the direction will move to the reactant side. Okay, so that's actually how you make the judgment. Okay, so the answer will be go to the left, making more reactants. Okay, that's actually how you answer these questions. All right. So everybody fine with this concept? Okay, now we're going to do some variants of these questions, okay? So if I say, let me pull out my Hangout so I can make sure you go through all these possible scenarios. Scenario number 2. If I add more H2 to my system, okay, the reaction will move to which side? Reactant or product side? Product, right? Because right now you actually increase your reactant, you have too many, right? You want to actually decrease the amount, therefore the only thing you can do is actually move to the product side. All right, so you know, this actually means your H2 or the pressure of your H2 is going to increase. Therefore, you want to move to the product side. Okay. Third question. If I increase the temperature of the system, okay, so let me write down. Then where will it move? Reactant or product? You will move to the reactant side, right? Because from the equation, you know that if you move to the product side, you are going to produce a lot of heat, right? So right now, what you do is actually, I actually increase the temperature of my system. Means actually I put in a lot of heat to the equations, right? So you want to actually minimize the heat generation. Therefore, you actually move to the reactant side, okay? All right. The fourth type of question that associated with this is that if I say today, I'm going to increase the pressure of my system. Can you predict where it's going to move? What would you do? What would the system move? To the product side, right? How do you know it's going to move to the product side? So here is actually the things you need to look into the total moles of gas molecule on the reactant product side. Okay, so if you look at the reactant side, how many moles you have in the gas form? 4 moles, right? It's 1 mole of your N2, 3 mole of your H2, right? So on the left-hand side, you have 4 gas molecules, right? On the right-hand side, on your product side, you only have 2 gas molecules, right? So the more gas molecule, the higher the pressure it will be, right? So if right now you increase the pressure, okay, you want to actually minimize the number of more gas molecules, then the reaction will actually move toward the product side, okay, to minimize the pressure, okay? Okay, so this is actually a very important concept, okay? These are the 4, pretty much the, okay. There's actually one more type, okay? That's a 5 different type of questions they can ask based on this setup. Okay. The very last type is actually if I throw in a catalyst into the system, how will it actually affect the equilibrium position? It won't, okay? So there's actually no change of your equilibrium positions. These are the 5 different type of questions that's going to associate with the Le Chatelet principle. All right, so no change of equilibrium position. Okay, so recap. Keywords, equilibrium position. Okay, so once you see that, that is actually related to your Le Chatelet principle. Okay, very clear, okay? Only 3 things will actually affect the equilibrium position: concentration, pressure, temperature. Okay, one thing that's going to be used to confuse you is called the catalyst. Okay, so those are the main things that you should know for the Le Chatelet principle. Is that clear? Okay, cool. That will actually conclude all the things that you need to know for chapter 12. Okay, so right now I would strongly encourage you to start to do your homework and quiz as early as possible this week. Okay, because the things you need to do during the weekend is to do the practice exam. Okay, so when you do the practice exam, make sure you're actually ready. Okay, you cannot bring the hangout with you. Okay, you need to actually do it only with your calculators, only with your pen. Okay, that's the only thing that you have before you do your practice exam. Okay, I think some of you actually have done questions about what are the calculators you can bring into CASA, right? So you can only bring the traditional non-graphical calculators into the CASA to do your midterm 1. All right. So the reason you want to do this is actually you want to make sure before you actually do your practice exam, before you do that, make sure you already memorize the 3-page equations. Okay, those equations on our hangout are essential. Okay, those equations are the equations you will use, okay, to really get a good score for your midterm 1. Okay, you need to actually memorize it. Okay, and then you really need to actually time yourself. If you don't do that, you feel very nervous when you actually walk into CASA. Okay, you need to really time yourself. Okay, and then all the things I can do and I can help is really tells you, okay, let's read the questions. Let's find the keyword. Let's figure out what equation that we need to use. Okay, and those are the things that you can actually learn from me. And I think those things are actually effective. All right. Okie dokie. So we're going to go to the review hangout. Okay, so in the review, we have 19 questions. Okay, but before it goes into those 19 questions, I want to actually answer a few of questions that you guys have posted on the team side. Okay, so let's look at the first one. So this is actually one of the equations that student posed. I feel that you can actually post everything that I need to have. Okay, so because it says actually which of the following plots represent the natural log data of rate constant versus reciprocal of absolute temperature of the data given above. I don't have the data, so I don't know which data is it. Okay, so, but I can guess the answer must be either this one or that one. Okay, so how do I know this? What are the keyword here? Okay, rate constant, and then the 1/t, right? So you can see all this plot has this natural log k and 1/t. Okay, so this is actually a question for chapter 11, right? Okay, so I'm going to actually tell you how I can actually decipher all these things quickly. This is 12. I want to go to the chapter 11. So this is actually our chapter 11 hangout, right? And then apparently it says natural log k, right? So the y-axis is actually natural log k, x-axis is 1/t, right? So every time you do natural log k, what will it actually tells you? Yeah, so once you see natural log, exponential is actually another thing that's going to associate with it, right? So with that in mind, in chapter 11, there's actually only two equations has exponential. Okay, one is this. One is actually your integrated rate law. Okay, that's one. The other one is actually here. Okay, and then that's actually how I actually think about the things. Okay, so I see the natural log, right? And the other important thing is actually the x-axis is actually 1/t, right? This is actually the only equation that has 1/t. So apparently it's actually testing this concept. Okay, so you need to actually really get familiar with, okay, and what are the equations that you have? So you can actually relocate these things quickly. Okay, so this will be the equation you're going to use. If you look at this equation, this is your y-axis, right? Your x-axis is actually 1/t, right? So I can write this as y equals to natural log a minus EA over R times 1/t, right? 1/t is actually your x. So this is actually y equals to natural log a minus EA over R times x. Okay. So this is what? This is a linear equation, right? Your slope is negative EA over R. Your intercept will give you natural log A. Okay. Any questions for this? Everybody follow the things I just said for less specific questions? So what is A? A is called a frequency factor, right? This is actually part of that question because it asks you about what is the actual EA what is actually your frequency factor. Okay, so let's go back to like questions. Okay, but these are the things that you need to actually see. Okay, so write the things down first. Okay, let's get back to this. So this question is actually plot out your natural log k versus 1 over t, right? So your y is your natural log k, your x is 1 over t. And then from the previous, we say the equation is natural log k equals to natural log a minus ea over r multiply your 1 over t. Okay, so this is actually your y, natural log a minus ea over r times this is actually your x. Okay, so what this means is actually if you plot out your natural log k versus 1 over t, you are going to get a linear line, right? Therefore, I know this cannot be your answer, that cannot be your answer. Okay, so only these two give you linear relationship, right? So you know the answer is either the top one or the bottom one, but I don't have the original data, right? So I can actually make a judgment. Okay, but the question is actually, but you are going to see the initial data, so you will know which one is actually which. They can describe the data that you have. Once you have this, it's asking you, okay, calculate the activation energy. That's one question. The other question is actually calculate the frequency factor A, right? So to calculate your activation energy, all you need to know is just your slope, right? So here you actually do the fitting for you and give you the slope, right? So what you need to do is actually, let's say, assuming this is actually the one that you have, then you know the slope is negative 9.56 times 10 to the negative 5. That's actually a slope from the fitting, right? It's going to equals to your EA over R, right? So you can calculate your EA by multiply the negative 9.56 times 10 to the negative 5 by the R, then you can get the answer for your activation energy. Okay? How do you get your A? You know the natural log A is going to equal to the intercept, which is this guy, which will give you 0.00225. Then you take the exponential on both sides. Okay, you can get your A is going to equals to the exponential. All right, so let's how you actually figure out the activation energy and then the frequency factor. All right, so recap. When you see these type of questions, okay, pay close attention to the x-axis and then the y-axis. Okay, so like you will see, it is describing something related to your natural log k and 1 over t. Okay, so once you see these two terms, you should know that it's actually testing your Arrhenius equation. Okay, the rate constant k is going to equals to exponential, is equals to like frequency factor A multiply the exponential minus EA over RT. Okay, so let's have how you can solve your A and also solve your EA. Okay. The other way you can actually find out the keyword is actually if you read through the question all the way to the end, right? Apparently is asking you the activation energy and then the frequency factor. There's actually only one equation have both terms. There's actually Arrhenius equation, right? So you can actually work this backwards. You know, there's actually only equation that have all these terms. Then it's actually into start from there. Okay, then trying to actually get back to this natural law. Okay, all you need to do is actually just take natural log on both sides, then you can get to this relationship. That's how you actually approach these questions. Okay, is that clear? All right. Second one, okay, this is actually also about the chapter 11. Okay, so you say if you see a diagram like this, okay, where the x-axis is called the reaction coordinate. Okay, you start from the left. Left is actually your reactant, right is actually your product, right? So A is actually your reactant. E is your product. Okay, so it is asking which step represent the activation energy. So how do you actually identify the step that's going to dictate your activation energy? So,
It's a slow step, but I guess.
yes, the slow step, right? So what makes it slow? So on the y-axis, what is the y? What is your y-axis on this plot? This is what? Energy, right? So that means actually if you go to higher, it means actually you need to go through a higher energy barrier. Okay, so the one with the highest energy barrier will be your rate determining step. Okay, so in this case, who will be this step, right? Because that is actually a step you need to actually hop over solid reaction will go forward. Okay, so it's actually this step will be actually your activation energy. Okay, so how do we calculate the activation energy? On this plot, okay, the way you calculate activation energy is actually you compare the energy difference between your highest energy to your reactant, okay, not to something else, has to reference to your reactant. That is actually how you calculate the activation energy on this plot, okay? What this tells you? Yeah, you start from a high energy reactant, go to a low energy product, right? So energy is always conserved, right? So when this thing happens, would this be a endothermic or exothermic reaction? Exothermic reaction, okay. This is actually one very important concept that you should know. Okay, so this is a okay. One more thing. What is B and D? Transition state, very good, okay. What is C? Huh? What is the name of C? Intermediate, okay. So far, so good. How do you actually differentiate it is an intermediate or transition state? Yeah, the peak is actually transition state. Then the valley is the intermediate. Okay, so you need to actually know what each symbol means because yeah, I think there's actually questions on our review. Okay, there's actually a question actually associated with this concept. Okay. You need to know your y-axis, the E is actually for the energy, okay, of each species, right? And then on this plot, you have multiple different species. Well, A is actually your reactant. B and D is your transition state. C is a intermediate. E is your product, right? And then you can see that the energy of your E is actually lower than the reactant A, okay? Telling you that the overall reaction is exothermic, all right? I can also draw something like this, right? Okay, I can label A, B, C, D, E, F, and G, right? Again, X is actual energy, Y axis is just reaction coordinate. Okay, so if you look at this plot, A is your reactant, right? G is the overall reaction is endothermic, right? C and E is your, good. And then B, D, F is your, which one is actually your rate limiting step? E to F, right? Because this is actually the one, I guess this is actually not very good drawing. Maybe this will be more clear. Right, so this step will be actually your rate limiting step, right? And this will be your activation energy. Okay, and then this will tell you it is actually a endothermic reaction. Okay, everybody have a better idea about this plot? Okay, good. Okay, let's look at these questions too. Okay, so it says hydrogen iodide Hi decompose into gas phase to produce H2 and I2. The value of the rate constant K for the reaction was measured at several different temperatures, as the data showing below. What is the value of activation energy? Okay, so keyword is what? Activation energy, right? So what is the equation that you need to use? The Arrhenius equations, right? So you need to actually start to memorize this equation, okay? So that you feel confident when you see the question, you know how to actually start, okay? So K is going to equals to A multiply exponential minus EA over R times T, right? That is actually equation that you know you need to use, okay? In this specific questions, it provide you different K, right? And different temperature, and asks you to calculate the activation energy. Okay, so what you can do is actually, it's kind of similar when we actually write out the question for the red law, okay? So from the first equation, you can write the K is 6.23 times 10 to the negative 7. It's going to equals to frequency factor. You don't know at this moment, you just write a capital A over there times exponential minus EA is actually the term that you want to calculate, right? Divided by R is actually just a constant, okay? Times your T, in this case, will be 555, right? So when you write out this equation, how many unknown do you have? 2, right? One is actually your frequency factor A. The other one is actually your EA, right? So you can write out equation for this. Then write out the equation for the other three. It's the same thing, right? So what you're going to do is actually you're going to write out 1.16 times 10 to the negative 5 equals to A times exponential minus EA divided by R times 600. Okay, so now you have two unknown. You have two equations. Can you actually solve for your A? Can you actually solve for your EA? Okay, that's all you need to do. Okay, so again, the key is what? Key is actually, can you recognize the keyword is the activation energy? And once you see the activation energy, you should actually go to the Arrhenius equation. Right, once you know the Arrhenius equation, then based on the data that you have in the questions, I assume everybody should be able to write out this question, these two equations quickly, right? And then you can just solve for your A and solve for your EA. Okay, that will be actually how you address this specific question. All right. Any questions for this? Okay, so if not, then let's go to the other one. Wood runs about 50 times more rapidly at 25 degrees C than when it was stored at 6 degrees C. Determine the overall activation energy for the process responsible for its decomposition. What is the keyword? Activation energy, right? So Arrhenius equation. Okay, so here it actually says, there's actually another hint here. It's actually have two temperatures, right? So let's actually only one equations. Okay, that's going to including two temperatures. Okay, so if you go back to our hangout, wrong one. This is actually the only one that gives you two temperatures. Natural K1 over K2 equals to EA over R, 1 over T2 minus 1 over T1. This is actually only equation. Okay, every time you see two temperatures, this is actually a go-to equation. Okay. So keyword here is actually two temperature and then activation energy or two rate constant. Okay, all of them is actually telling you you should use this equation. All right. So get back to here. Natural log K1 over K2 equals to EA over R, 1 over T2 minus 1 over T1. Okay. So right now we know you have two temperature, right? One is 25 degrees C, one is 6 degrees C. Okay, and then from the description, it says the rate constant is actually 50 times faster at 25 degrees C compared to like 60 degrees C1, right? That means if the rate constant is K for your 60 degrees C, for 25 degrees C, it will be 50 times faster, right? So I assume everybody should be able to write the things out, right? So you have this T1, K1, T2, K2, right? So all you do is actually plug these things. Okay, so let's say this is actually our K1. Okay, then this will be 50 times K1, right? This is actually my T1. This will be your T2. Okay, so with that being said, you know, you can put natural log. K1 will be just K1, right? K2 will be 50 times of K1. That's why you have on the left-hand side, right? On the right-hand side will be equals to EA is the things they want to solve. R is just a constant. 1 over T2. T2 is 25 degrees C into convert into Kelvin, right? So it's actually 298, right? Minus 1 over 6 degrees C, there will be 279, right? Then K1 cancels out, right? R is actually a constant. Use this equation to calculate your EA. Okay, that's how you solve this question. All right. Any questions so far? Okay, if not, then we can actually go back to our Hangout. Okay, so the Hangout, we have 19 questions here. These 19 questions compose actually 3 sections. Okay, so question number 1 to 7. This is actually for your chapter 10. 8 to 13, 11, and then 14 to 19 is chapter 12. Okay, so we're going to go backwards. Okay, we'll go through the questions for chapter 12 today, and then on Thursday, we want to go through the question for chapter 11 and 10. All right. Okay, so let's read through these questions quickly. The water-gas reaction is an extremely important one in industry. Okay, so it shows this specific reaction. At a given temperature, the Kp is 2.7. If 0.13 mole of CO, 0.56 mole of H2O, 0.62 of CO2, and 0.43 mole of H2 are placed in a 2-liter flask, okay, then it's going to actually calculate the QP. Okay, so you're going to see a multiple options. Okay, and it's going to show up these things called QP. Okay. So if you see this QP appear in your questions, 100% it is a question that is going to ask you to compare your QP to your KP and predict where the reaction is going to move. Okay. So how do you calculate the QP for this reaction? So let's go to okay, so the first thing you need to do is actually you need to write this, okay. CO in the gas form plus H2O in the gas form. That's going to give you CO2 in the gas form plus H2 in the gas form. Okay. So the chemical quotient Q can be calculated using the equation that is the pressure of your product over the pressure of your reactant. Right? So you need to know how to actually write out your chemical quotient properly. Okay, and then it also tells you your Kp is equals to 2.7. Okay. So if you read your question carefully, it says, okay, you have 0.13 mole of CO, 0.56 mole of H2O, 0.6 mole of CO2, and 0.43 mole of H2, right? Those are the numbers that you will be using to calculate your QP. Okay, so how do you actually calculate your QP? How to get your P? Okay, so we all know this, right? PV equals to MRT. Okay, this one is a what? Anyone know what this is? The ideal gas law, right? Okay, so from this law, you know the P is actually a function of this, right? Okay, so in order to calculate your P, you need to use the term that's actually N over V, okay, times a constant. Okay, R and T is actually a constant, okay, for a given temperature, right? So this is actually a term that you need to actually calculate. Okay. So if you read the question, it actually tells you how many mole of each species that you have within a 2-liter container, right? That 2 liter is actually the volume of the gas, right? Or the volume of the container, right? Therefore, you know your PCO2 more proportional to PCO2 is 0.62 divided by 2, right? So you know it's going to equal to 0.31 for your PCO2. Okay. pH2 more proportional to 0.43 divided by 2, that's 0.215. Okay. And then you also have a PCO, which is going to give you a value of 0.13 divided by 2, that's 0.065. Very last one is actually a pressure of your H2O going to proportional to 0.56 divided by 2, that's 0.28. Okay, so let's how you actually compute, okay, your pressure. Okay, basically is actually moles of your gas molecule divided by the volume. Okay, so once you have all these things, what you do is actually put all this information back to the equations, right? Therefore, you're going to have 0.31 multiply 0.215 divided by 0.065 and then 0.28. After you do that calculation, you're going to get a value of 3.7. Okay, so now you have your QP is 3.7, right? And then your KP is 2.7. What does that mean? If you have you have too many product, right? So eventually KP is actually the final status that you want to have, right? We can always consider this portion is actually product over reactant, right? The larger the number, the more product you're going to have. Okay, so in the current status, your Q telling you have too many product, but eventually you want to go to K. Okay, K have less product, right? So in order to actually go to your K, the reaction will do what? It will going to move to the reactant side to deplete the product, to deplete the excess product that it has. Okay, so the answer will be, after you do this computation, right, you can actually calculate what the QP is, and you should know that the reaction will actually go to the left, which is actually the reactant. Okay. Any questions so far? Okay, so if not, let's recap these questions. Okay. So this type of question typically give you a lot of information of every single individual pieces, right? And then it's going to give you the value of K. Okay, so and then in your your options A, B, C, D, you're going to see a term called Q, right? So that is actually a standard questions that want you to compare your Q and K. Okay, if your Q is larger than K, means you have too much product. Okay, you want to actually minimize product, you want to move to the reactant side. Okay. If your Q is larger than K, is too much product. Therefore, you're going to move to the left-hand side or to the right-hand side. Okay. If your Q is smaller than K, too few or too less product, then you want to actually produce more, then you're going to move to the product side. Okay, so this actually kind of the conceptual things that you should actually have. Okay. So with that in mind, the next thing you do is actually you should be able to know, based on the equation, can you actually write out the proper equation to calculate your chemical quotient Q. Okay, so this is actually why these things actually matters. Okay, and then once you can write out your chemical quotient Q, can you actually compute the proper values for each individual terms, right? So let's actually where you want to have some concept of this PV equals to MRT. Okay, you can actually compute your P in terms of N over V. Okay, so once you have that concept, then you can compute your QP. Then you can compare to your KP. Then you can actually predict where the direction going to move to. Okay, so let's actually overall conceptual flow for this type of questions. Is that clear? Okay, so if I'm going too fast, okay, stop me. It's okay. Okay. The important thing is actually you understand all the things. Okay, so another important thing that we discussed in chapter 12 is actually the change of equilibrium constant K or KEQ. Okay, so the example that we give you is actually if you have AA plus BB, that give you CC plus DD. Okay, then you have associated equilibrium constant K. Okay, if you flip the reaction, what happened to your K? If you do DD plus CC, if you AA plus BB, then yeah, this become K to the -1 power, right? Okay. The third one is actually if you multiply a coefficient to your equation. For example, if you do NDD plus NCC, give you NAA plus NBB, then here will be K to the -nth power, right? You need to actually multiply coefficient to your exponent. Okay, so those are the things that we have learned, right? And also, if you have two equations add up, then the new equilibrium constant K will be just simple a product of the other two equations, right? So those are the things that we have learned in the past lecture, okay? So we're going to use the same concept right here, okay? So in this question, it says for a certain temperature, the Kp for a reaction is this. Calculate the value of Kp for another equation. Okay, so this is actually a very typical questions, okay? It gives you an equation, it gives you a K, okay? And then it gives you another equation, X to actually compute the equilibrium constant for that specific equation, right? So let's actually time when to actually apply these four rules here, okay? So what you need to do is actually recompare, okay, what's the difference between these two equations, okay? So originally you have N2 gas plus 3H2 gas. That give you 2NH3. You have a K equals to 784.8. Now the target equation is actually this. Right, you want to actually recalculate the equilibrium constant for this specific target equation, right? So what you will need to do is actually want to compare these two. Okay, so what is the difference between the two? Yeah, So the second equation is actually the same as the first one, except it multiply a coefficient 1/2, right? So what you really do is actually you multiply 1/2 here, right? And then from the concept we just went through, then the k new to equals to the original k multiply 1/2 in its exponent, right? So it will give you that relationship. So this is going to give you 784.8. You take the square root of that, right? And this is going to give you a value of 28, I think. Yeah, 28.02. Okay, so this is actually how you solve this problem. Okay, it's actually very simple, right? So if you know there's only 4 rules, then you need to actually 3 rules, right? You flip, then you put a -1 in the exponent, right? If you multiply coefficient, then you actually multiply coefficient at the exponent, right? If you add up 2 equations, it's just product of the equilibrium constant. Yeah, so those are the 3 rules that you need to actually memorize. Okay. So that's actually how you solve question number 15. Okay, 16. Phosphorus pentachloride decompose into phosphorus trichloride and chlorine gas at elevated temperatures by the following reactions. If Kc is 2.9 at 300 K, what is the value of Kp at the same temperature? Okay, so this is a Kc Kp conversion. Okay, so apparently it tells you what the Kc is for these specific reactions, right? And then it wants you to calculate the value of Kp, right? So this again comes back to the equation that I asked you to memorize. The way you convert the Kp and Kc is that the Kp is going to equal to Kc multiply R times T to the delta n's power, right? So now you need to actually know how to compute delta n, okay? Because you know Kc is 2.9, R is just a gas constant, right? T is 300 degrees C convert to K, right? So it's actually 593 K. Okay. So now the things that you don't know yet is actually the delta N. If you know the delta N, then you can compute your Kp directly. Everybody follow this? Okay, so how do you compute the delta N? So the way you compute delta N is what? You want to actually identify the gas molecule in your equation for both your reactant and the product side, right? So this is gas, and that is gas, right? So number of gas molecule on your product side is 2, right? You have 1 PCl3 and 1 Cl2. So the N of the gas molecule on the product side total is 2. On the reactant side is 1, right? So your delta N is equals to 2 minus 1, which is going to equals to 1. Okay? That means your Kp can be computed using 2.9 times the R. Make sure you use the correct one, okay? 0.08206 times T is 5. Sorry, this should be 557, 573, okay? And then they will give you a value of 136.4. Okay, so that's actually how you compute your Kp. Okay? Yes. So 573, how do I get the 573 is coming from, I convert my degree C plus 273 so that I can convert the C to K. Okay, so all the temperature you use for all the calculations has a unit of K. Okay, and the way you convert your C to K is actually add 273 to your degree C, so you can get the unit of K. Yes. So the delta N is computed by the mole sum of your product in the gas bond minus lag in the reactant part. Okay, so if you look at the reaction again here, from the product side, you have 1 mole of PCl3, 1 mole of CO2. So the total gas sum is 2. On the reactant side is only 1. So 2 minus 1, they give you a value of 1 for your delta N. Okay, so let's say you have something else. You have this. Okay, let's say this is actually the equation that you have where A, B, and C they are in the gas form. Okay, the delta N here will be what? 6 minus 5. Okay, is that clear? All right, any other questions? How do I know I should use 0.082 or the? Okay, so this is actually a one specific locations that you need to actually use this. Okay, because it converts the pressure to the concentration. Okay, so the pressure typically have ATM. Okay, and then the concentration typically molarity. This is actually only thing, probably is actually only place that you need to use 0.08206. Okay, for the activation energy for that part, okay, that one doesn't actually involve the transition between concentration and pressure. Then there you use 8.314. Okay, so every time you see the pressure start to show up, this probably is actually R you want to use. Okay, any other questions? Okay, so if now let's go to where? Any other questions? Yeah, so if let's say pure solid or pure liquid, it does not go into your chemical equations, right? Yeah, so, and then when we calculate this delta N here, it's only for the gas molecule. Okay, because only gas molecule will actually contribute significantly to the pressure. Okay, way more than your liquid or than your solid. Okay, so that's why we only compute delta N for the gas molecule. All right. Okay, any other questions? There's a good one though. Yes. What's the delta N for this case? 1, right? 7 minus 6, 1. Okay, this is in the solid form, right? Ignore it. Solid doesn't contribute to the pressure at all. Solid, liquid, forget about it. You are targeting the gas. Okay? You only want gas. Okay, when you actually try to convert the Kp to Kc, gas molecule is actually your only target. Okay. Only gas will contribute significantly to the pressure. Okay. All right, so okay, so this one is actually trying to actually test whether you can understand the description of the questions. Okay, you say there's actually a chemical reaction H2 plus I2 give you 2HI, whereas it has a Kp of 54. An equilibrium mixture at this temperature was bound to contain that much ATN of H2, that much ATN of HI. Compute the equilibrium pressure for your I2, right? So again, write out these things first. So you know your Kp is going to equals to the pressure of your Hi to the second power over the pressure of your H2 first power, pressure of your I2 first power. And this whole thing will give you a value of 54. Right? So, and one thing we do a lot is actually we want to actually know, okay, the information they provide belongs to what status, right? So it says you have a equilibrium mixture at a given temperature, okay, where the pressure of your H2 is 0.672, right? So where should I actually put that number? At equilibrium, right? So you know it should be 0.672 here, right? And then the other one is what? I2, this is also at equilibrium, right? So I know I need to put 2.99 right here, right? And then what you are looking for, or what the question is actually looking for, is they want to know the pressure of I2, right? So you know this guy is actually this guy, right? It's actually at equilibrium. Okay, and then this guy is this guy, and this is lab. Okay, so if I put everything in, then I know it will be 2.99 to the second power divided by PHI is 0.672, and then times the pressure of your I2. This whole term will give you a value of 54. Right? And then it's asking for the PI2, right? So you know your PI2 will simply equals to 2.99 seconds power divided by 0.672 multiply 54. That's going to give you a value of 0.25. Okay, so again, this is a question that tests how well you can read the questions. Okay, so you should know that the value it provides belongs to the status of your species at equilibrium, right? And then you should also know that how to write your chemical equilibrium equation properly, okay? And with these two information together, you will be able to actually calculate the pressure of your I2 without any problem. All right, so let's actually for question number 17. Any questions? Yeah, so because here you already know, this is what, even though I write the ice table, right? Since you know this keyword, there's actually equilibrium mixture, right? That means actually the information it provides belongs to at equilibrium, right? And these are the values you can use directly for your equilibrium constant equation. Right, so with that in mind, then you don't need to actually go, you don't need any other information. You can already solve your problem, right? So you know you don't need to actually worry about ice table at all. The reason I write is ICE simply is actually let you see better where you can actually position those numbers in. Okay, and then the student will get confused, right? You always can get all different numbers, right? So when can I actually apply those numbers to my equation? Okay, it's not very clear to many students, right? The only reason we write this ICE is to let you see you can only apply the number at equilibrium to your equilibrium constant equation. Okay, and this is actually a very important concept that everybody should know. Otherwise, we won't be able to do a calculation properly. Okay, so we need to practice this over and over again. All right, any other questions? Okay, so if not, I guess we have only time for the very last questions, okay? At a given temperature, you have 4.86 atm of H2, 3.83 atm of CO2 are mixed and allowed to come to equilibrium. Okay, so this sentence, okay, mixed and allowed to come to equilibrium. What does this tell you? Yeah, I need to do the ice table, right? And the information you provide there belongs to the initial condition, right? It is not equilibrium, okay? Because it says the keyword is mixed and allowed to react, right? So whatever number we have here belongs to your I, okay? So let me write down the equation first. It is H2 plus Cl2 that give you HCl, 2HCl, okay? So ICE. In the beginning, I have 4.86, 3.83, okay? And then it says the equilibrium pressure of HCl is 1.239. Where should I put that 1.239? At equilibrium, right? So you know it has to be 1.239 here, right? Okay, so this is where the ice table is going to be meaningful, right? Because you have some initial condition, you have some information at the equilibrium, right? So here we're going to say, okay, some change is going to happen, right? And then that change will be, let's say you have minus x here, minus x here. What should you put here? Plus 2x, right? So here should be plus 2x. Okay, so once you reach equilibrium, what you're going to have is 4.86 minus x for your H2, 3.83 minus x for your Cl2, okay? And then your 2x is simply equals to 1.239. Everybody follow this? Okay, so from here, you can just solve for your x, right? So x is going to equals to 0.6195, right? Okay, so once you have this, then you know this guy, okay? The pressure of your H2 at equilibrium will equals to 4.86 minus 0.6195, which is going to have a value of 4.2405. Pressure of your CO2 will equals to 3.83 minus 0.6195, which is going to have a value of 3.2105. Okay. The question is actually asking for the Kp, right? So you should know that the Kp is going to equals to the pressure of your HCl to the second power over the pressure of your H2, pressure of your I2 to the first power. And the pressure of your CO2 at equilibrium is 1.239 to the second power. Pressure of your H2 is 4.2405 first power, and then CO2 will be 3.2105 first power. Okay, so after you compute all this, it's going to give you a value of 0.113, and that will be actually the value for your Kp. Okay, so this is actually how you solve this question. Sorry, I'm already delayed, but I guess I will stop here. And then if you have more questions, feel free to email me. Okay, or you can post the questions on the Teams. I will actually go through those questions in the next lecture. Okay, thank you.
I had a quick question.
Mhm.
AP,
Yes.
so